Hey everybody, welcome to today's video lesson on enthalpy of solution. So let's consider a lab in which we're dissolving potassium hydroxide in water, and we're going to run a couple of trials changing the amount of potassium hydroxide that we use. In trial one, we put about 30 milliliters of water in our beaker, and its mass was 30.40 grams, and here's the mass of potassium hydroxide that we used. Okay, so these quantities are both in the beaker, and the thermometer gives an initial temperature reading of 22.1, but as we stir and the potassium hydroxide dissolves, as that physical change occurs, we see a temperature change, and the temperature goes up. It goes up to 29 degrees. So the delta T, which represents change in temperature, is just the absolute value of the difference between these two. And that would be 6.9 degrees Celsius. Now I'm going to make myself a note that the temp went up, and that means I know the dissolving process was exothermic. All right, now in the analysis, we're asked to calculate the magnitude of heat energy involved in the dissolution of KOH. Dissolution, fancy name for dissolving. And heat energy is our Q. So we're going to use our MCAT equation. Q equals M times C times delta T. But I want you to remember that the temperature that we're taking, the two temperatures, initial and final, are the temperature of the surroundings. Remember, we've said that you cannot insert your thermometer or your temperature probe and make it land exclusively on these molecules, the system. All you can do is measure what the surroundings are doing. So our delta T is that of the surroundings, and that means what we're going to calculate here is the heat energy observed of the surroundings. Okay, the specific heat capacity of the surroundings. Okay, again, our surroundings is a solution, and while we may not know that exact value, it is okay in these labs to assume that this value is the same as that of pure water. All right, lastly, we need to plug in mass of the surroundings. And the surroundings is literally everything we put in our beaker, everything in the cup. So the mass of the surroundings is not simply the water, it's the water and the KOH that we put in there. The specific heat constant, we're fudging a little, but we're going to use the specific heat capacity for water. And then our temperature change is the difference between these two numbers. So here are the values that we're plugging in. And you see that the grams in our mass recording cancels out, and the degrees Celsius in our change in temperature recording cancels out. And when I multiply through, I get 937.68 joules of heat energy. Joule is a unit for heat. All right, now we are asked to run a second trial. And in our second trial, we're going to use the same volume of water. Okay, but this time its mass is a little bit different. Okay, I'm shooting for 30 milliliters. I'm not exact. And then I'm virtually doubling the amount of potassium hydroxide. So this time in my beaker, I've got water, potassium hydroxide. My temperature starts out 22.5, and look, it goes up significantly this time. The change in temperature is the absolute value of the difference of these two, initial or starting temperature and the final temperature. And that's 12.5 degrees Celsius. And again, I'm going to note the temp went up. So this is an exothermic dissolving process. Right, now when I calculate the heat energy of dissolution, the Q, of my surroundings, I have these two numbers added together to give me the mass of everything in my beaker. Here's my specific heat capacity, constant, and my temperature change. Here are the values I'm going to plug in. And this time, with that larger amount of potassium hydroxide, the heat energy that was observed has in fact increased. All right, so in these two trials, I get two different heat energy values, but again, that's because the amount of solute that I used changed. All right, so here is the thing, guys. This Q, this heat energy that is observed and measured in the lab is for a specific trial. It is unique to each trial depending on how much solute you use. What is more helpful to me is a value known as enthalpy of solution. And enthalpy of solution is denoted this way. This delta sign, Greek letter delta, means change in enthalpy or change in heat energy of the system. So this is really the enthalpy or enthalpy change of a dissolving process. And to calculate this, we're going to take the heat energy that we measure in the lab, expressed in kilojoules, and we're going to divide it by the moles of solute. So let's do that for each of our trials. In trial 1, we had 2.08 grams of the solute. I'm going to use my periodic table and molar mass to convert that into moles of solute. And then I'm going to take my heat energy, my Q, and instead of keeping it in joules, it is customary to change that into kilojoules by dividing by 1,000. To calculate the enthalpy change or enthalpy of solution, those are kind of synonymous, I'm going to take that value of Q and divide it by the moles of solute. And when I divide, I get 25, I'm going to round here to 3 sigdigs. Here, when I get to the end, it's appropriate to do my rounding. My mass had 3 sigdigs, so this is 25.3 kilojoules per mole of potassium hydroxide. Now, I'm not quite done. This last bit is possibly the most important part. I acknowledged that this was an exothermic dissolving process. I saw that because the surroundings got hot. Well, whenever you have an exothermic energy change, that means the system is undergoing a negative change in its energy. And we have to put this negative sign here for the delta H. So negative 25.3 kilojoules per mole of KOH. That's the value I get for trial 1. Let's see what we get for trial 2. Trial 2 used 4.03 grams of potassium hydroxide. Use molar mass to change that into moles of solute, and then take the Q that was measured in the lab and dividing by 1,000 to express it in kilojoules. Now my enthalpy of solution, or change in enthalpy, is the value of Q for that reaction divided by the moles of solute I used in that reaction. And that quotient turns out to be 25.4 kilojoules per mole of KOH. Again, don't forget this step. This dissolving process was exothermic, so for the delta H, I have to denote that with a negative sign on my enthalpy of solution value. Trial 1 and trial 2, notice that they are virtually the same, certainly close enough given that we're doing lab work without the world's most precise instruments. So I get the same value for enthalpy of solution for this particular solute. Okay, guys, I hope that was helpful.